This is joint work between Brave, the University of Illinois at Chicago, and Imperial College at London. So in a single slide, this talk is about how you can manipulate resource pools and browsers to reintroduce tracking techniques that we thought we got rid of by partitioning. So in general, like the general tracking defense in browsers is to partition. So if you have the same resource embedded on two different websites, they get their own resources, and that prevents the two sites, that resource from linking the two visits. However, there's many things in browsers that aren't partitioned. These are mostly like implementation resources, things like socket pools, things like that. And if you're clever, you can use these to track people again across sites. These kinds of techniques have been known for a long time, but this work shows that they're both very practical. They're much easier than kind of assumed previously, and also they're far more vectors than previously identified too. So in this talk, I'll first define what a pool party attack is. I'll talk through some concrete examples in popular web browsers. I'll show how we measured that they are actually practical for real-world attacks, and then conclude. So first, what is a pool party attack? So a pool party attack kind of has three properties. It's a kind of covert channel that exists in web browsers across contexts. So a context might be two different sites or two different browser profiles, things like that, two different applications, but across logically distinct contexts. And they build this covert channel by abusing resource pools that are limited, and that you can only create so many of them, but they're unpartitioned by context. So as a toy example, let's just assume two different sites, site A and site B, and they're going to create a pool party attack by using a pretend optimization that only one video can be playing in the browser at a time. So if site A wants to transmit a very small identifier to site B, in general, the browser tries to prevent this, but the site A can manipulate this resource pool of how many videos can be playing in the following manner. If they want to transmit a 1, it can play. Site B will try to play the video and see that it can't, and so no, that's a 1. If site A wants to transmit a 0, it won't play, and site B will see that it can play and record a 0, et cetera, et cetera, et cetera. Again, the four properties here that are kind of core to this, though, are that the resource pool is unpartitioned. So again, both sites are pulling from the same single video that can be playing in this example. The sites know how big the pool is, so it's predictable based on other information that the site has, like the user agent string, something like that. Sites are not generally restricted to reading or writing from the covert channel, other than the global limit. Sites can play videos arbitrarily. And then last, sites can detect when the resource pool has been, or the cap has been hit. So where do these things kind of exist for real in browsers? Like I mentioned, connection pools, file handle pools, thread pools, limits on how many requests can be in the air at one time, different types of UI where the browser may impose a restriction on how many things can be happening of that type at a time. But there's a lot of these things in browsers. It's a real threat. In the previous example, like that's a very slow channel. If you can only read and write 1 bit at a time, that's going to take a long time to transmit an identifier. And so if you're an attacker, what do you want to make this a practical attack? You want a large resource pool so you can read and write a lot of information at the same time. So the more resources that are in this pool, the faster you can communicate across it. You generally want unpopular resources. So if websites if there's a lot of benign use of this resource pool, it's going to be harder to communicate across it because it's going to be a very noisy channel. And then last, you want the ability to release or pull resources out of the pool very quickly so you can communicate across it more quickly. All right, so that's broadly what we're calling a pool party attack. Now, where do these things actually exist in browsers? So we looked at 6 different browser engines, 3 of which are Chromium browsers, 2 of which Gecko, Firefox, and Tor, and then Safari, which is the main popular WebKit browser at the time we did this study. We audited these things or these browsers in a variety of ways. So one, just reading through the available source code, consulting developers, consulting engineers on the teams to try to find these limited and unpartitioned resource pools. And the 3 that we identified as being the most practical for communication are WebSockets. WebSockets are an API that allow kind of like a TCP-like communication, a persistent communication channel between a server and a website. Web workers, which are kind of sort of like sub-processes. You can execute code without bothering the main event loop. And then last, servers and events, which are kind of like an API that is kind of a way of servers to push notifications to pages. These are all implemented in popular browsers. And so what do we find? The cells here are the size of the resource pool in the relevant browser. I want to point out 2 things here. One is that in Firefox, not only are these resource pools unpartitioned by site, so different sites pull from the same resource pool, but different profiles also pull from this resource pool. So if you have a private window and a not private window, they can create, you can create a covert channel to communicate across those 2 things like that. It's a problem. The other thing is that as of publication, these 3 examples of the problem have been fixed. The other browsers are working on fixes and trying to fix it, partially through addressing them in the standards. All right, so those are the pool party attacks we identified in browsers. Now, how do we know that these things are actually practical? So when we say practical, we care about 3 things. How much information can you shove through the channel? How often does the information that you send get received correctly? And how stable is it? Are there a bunch of other people talking through the channel at the same time? And so in this table, I'm presenting the bandwidth, which is how fast can you communicate, and the consistency, how often do you get information correctly when you read it and write it back, or write it and read it back. And so these measurements are for sending a 35-bit identifier across the channel, and just averages over 100 measurements. The things I mostly want to emphasize here are not the exact numbers, but that these are all extremely practical attacks. The setup column is some preamble communication for describing or figuring out who's going to be sending and who's going to be receiving. And the send is the actual 35 bits going across the channel. But all of these things take less than 10 seconds, and in some forms of the attack, less than a second to communicate. So they're extremely practical. Then how stable are these channels? Basically, like I said, stability is the inverse of how popular they are. So if you're using a feature that's very popular on the web, that's going to be a very noisy channel, and so it's going to be very hard to communicate across it. If you're using a very unpopular feature, then you have a very stable channel or a very quiet channel. Most of these features are not widely used, but you can see server-side events are extremely uncommon on the web, and so that forms the most practical channel that we saw. But in general, you have these are practical attacks. So to wrap up, what can we say about this? There are a couple of conclusions from the paper. These are not the only attack vectors that we found. All the browsers we measured have other unpartitioned global resource pools. So in both Chromium Gecko browsers, for example, a DNS resolver, you can only have 64 simultaneous requests at a time. If you're communicating through an HTTP proxy, there's a cap on how many requests can be in the air at the time. The WebKit ones here are maybe particularly interesting. If you're using WebKit for Mac, or like the Safari build of WebKit, these caps are not here, but if you're using certain non-common or less common builds, so the GTK build of WebKit, for example, you get these other pool party vulnerable attacks. We're also sure this is not an exhaustive list. These are the things that we found in our auditing, but I'm sure these are not exhaustive. So how can you defend against this? Again, Safari and Brave have shipped fixes for the ones we identified. In general, there's 2 ways you can fix these things. You can partition, so every site gets its own set of allocations. So if one site exhausts the pool, other sites aren't affected. That prevents you from communicating. Or you can remove the global cap, and so effectively just allow an unlimited number of communications. You still have, like at the extremes, the possibility of exhausting all resources on the system, but that becomes a much more difficult attack to carry out, and particularly something that users will notice if you start crashing all the apps on their device. But either of these attacks would work, and you can do both of them too. All right, so thank you very much for your time. There's some other details in the paper I just want to mention. So the algorithmic details for how we figure out who's talking and who's receiving, some comparisons to other ways that tracking are done on the web, and some other details about the measurement. Thanks very much for your time.